Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our lecture 7 with an introduction to deep learning. And this is really a very quick introduction because normally, as in other topics in this course, you would see that deep learning needs at least 3 days from morning till evening to really be understood if you have, let's say, a crash course I was teaching earlier and other occasions. And usually even these courses on deep learning were then on top also already being based on material on another machine learning course, which is usually also 3 days at least, covering the basics. So hence this is a high performance computing course, and still we want to dive now into applications. In this sense also, congratulations, you have basically passed all the technical elements of the course from a certain perspective covering the basics. Now we use these techniques and learn more, of course, also by applying them more and more in different application areas like computation fluid dynamics, which is one of the emphases here on the course, but also then with artificial neural networks, with deep learning, machine learning techniques used in these application fields. So still, today it's important to cover some of the basics in deep learning. So we will start effectively with machine learning instead of deep learning, and I will show you also the difference today. Let us, before we dive into this material of this course, however, review what we had the last time, because lecture 6 was also directly related why deep learning is so successful today. If you remember, we looked in lecture 6 a little bit on the top 500 list. You see that here on the left-hand side with all the nice systems in the world that cost a lot of money and are also our top machines, at least those we know. We also have perhaps some systems in the world that we don't know. But in order to be listed here, you have to be known and you have to deliver essentially a benchmark and apply for the list, and then the ranking is usually twice a year determined. So one takeaway message really from lecture 6 then, which was related to accelerators and graphical processing units, is really now firstly that almost all of these systems, right, that are in the top 500 and then in the top 10 especially, are fueled by some sort of accelerator. And we see here the first exascale system we know with an AMD Instinct card. We have here the second one, which is an Intel Data Center GPU Max. We have an NVIDIA dominance in the list. We see here H100, which stands for Hopper cards, Ampere cards, and also even Volta cards are still in the list, right? So many systems are fueled by NVIDIA. This is not a secret, but interesting for us in the HPC domain is now that this market dominance in a way is more and more vanishing, perhaps because there are more and more AMD systems and more other vendors coming up to speed and also delivering accelerators. So it's getting a bit more heterogeneous, as we would call that. And this is certainly also nice when we think about the price that these cards have. This is quite a very costly endeavor. In one of the earlier lectures, I think I said, normally there was always one big element in price in HPC systems, and this was the InfiniBand, the interconnects, and so on. Really getting every node with every node fully connected, or as you remember from some of the courses, with these trees and so on. Today we have more Dragonfly, but still it's a very costly element to actually interconnect all these systems. However, the second, let's say, really cost-intensive part now is these NVIDIA cards that you have, right? So GPUs, etc. Hence, why is that so? You can look here a little bit into one of the nodes of the Jülich Supercomputing Center system, Juvels, that we also had previously in the course. Remember, it's one of the modular supercomputer I was alluding to, where one of these nodes, we have 936 here of these nodes all together here in these racks, where so many of them have also all of them 4, right? So you have to multiply this, coming around to 3,744 GPUs. So in the end, lots of GPUs, and we want to use them in parallel. This is, of course, something what we also do with tool sets. I will come to this today when we, for instance, thinking about also using AI at scale with deep learning. Then also looking more deeply in the other systems, like for instance, the Summit system, which is here also still in the top 500. It's on place 7, but it doesn't matter. It's a good illustration also what's happening, let's say, beyond just saying it's 4 per node. Here you have 6 per node because it's another system. Hence, every of these HPC systems in one way or another have a different architecture mostly. And this can be related to the amount of memory you have alongside the GPUs. You see that here, for instance, the HBM2 memory per GPU here, or the interconnect between the different GPUs. We have here an NVLink interconnect between the different GPUs, so they can also really fast, communicate together. Still, it remains a fact that we have the host CPU here. This is something which more and more is vanishing, and especially if you now see some of the newer systems that come along, they sort of have a very good connection between essentially the main memory of the CPUs, the host CPUs, and also the main memory of the GPU. So not directly, perhaps we would say a shared address space, more or less, but very, very good connected to each other, much better than in previous times. So let's say the hindrance that we were talking about, that everything has to be always going through the host CPU, then uploaded, etc., to the device memory, and then etc., etc. This is a little bit, let's say, worked on, so that new generation of these cards would be having almost a very high, throughput access to the host CPU from the device memory. And with this, also some of the programming paradigms will probably shift a little bit of exploiting this. But of course, not all vendors will have it. So still lots of heterogeneity, but also I think lecture 6 really have shown us. Then we also thought a little bit again, the whole idea of transferring this, and then getting the results back is exactly the point I was, alluding to. So that exactly this connection, luckily in newer cards now getting, let's say from the initial bottleneck, better and better supported now. But hence also the application specialists that are actually programming then, let's say solvers that programming applications for it also have to leverage this and have to work with this. And this means also maybe some different changes in applications again. However, I think that summarizes lecture 6. Of course, there were many different details, but in a way, I hope everybody of you is now familiar with GPUs. A nice topic where alone, like in deep learning, you can have a whole course, right? So GPUs could be definitively, especially now with all the heterogeneity, different toolkits from CUDA, ROC, and AMD, and so on, definitively a course on its own. Another idea would be having a deep learning course, and the university has this here. So I encourage you, if you have interest in this, of course, to think about this. If you have interest, if you like the topic, to think about this. Magnus in the faculty here was teaching, for instance, a deep learning course, and others as well. So please contact me if you have interest. I think that's really something very nicely fitting together also with HPC. Hence, here comes again the disclaimer before I start. This is not at all a whole deep learning course, right? We make here just a very short crash course in the basics of machine learning, really, in the terms of artificial neural networks, to understand a little bit of a very specific part of deep learning called convolutional networks. Deep learning alone is a topic which is so interesting, also with now thinking more about generative AI coming up, or transformers, which are, let's say, in research now, one of our cutting edge mechanisms for image recognition. So I think these are all topics where more and more we see that for deep learning, there could be whole professorships just on these topics, because it's a really, really broad topic these days. And all of them have the interesting factor that they really require HPC at scale. So, however, we start here with a shallow introduction, really, because, as I said earlier, this course doesn't have any prerequisites. So here we start with a so-called linear learning model. That is the simplest learning model you can have. It's a perceptron learning model getting quite long back in history. And then we will add to this more and more the ideas of combining different perceptrons, understanding why their interconnections are then basically a big factor also in terms of understanding the growth of trainable parameters. So of course, there will be some application example where I try to motivate this along the line, and you will see that the whole lecture, in a way, also part 2, will come back to this specific application scenario. Of course, MNIST, as it is called, this data set, in order to understand it, is really simple to understand and a very simple problem. It's just 10 digits to recognize. The data set is fairly, let's say, small in terms of number of pixels and so on, but it captures the essence of how to move, let's say, from a binary, let's say, problem to a 10-class problem, hence a multi-class classification, as we say, and then continue with some of the elements how to train an artificial neural networks. And this brings us to elements like backpropagations and optimization. But again, backpropagation alone, if you want to fully understand it with a chain rule and everything, takes you around 1 or 2 university lectures. So again, here, this is just a very short introduction. Lecture 2 then will build on that, and we'll see that the results we will basically getting out of, let's say, traditional machine learning can be beaten nowadays really with deep learning, at least when you have enough data. So we start a little bit to understand when we can also do, deep learning. We move away from shallow learning, as we call it, with the traditional machine learning approaches, to deep learning, and I will describe it more in detail than I had previously done. And then we have, again, our MNIST application example that will show us very nicely now the differences in this character of this convolutional neural network as a concrete idea of an architecture of a deep learning network. There are many, as I was talking to you before. There are, let's say, variants like residual networks. There are transformer architectures. So there are, let's say, many different architectures that you can employ now with deep learning. And this is just one of it that we will capture here with the convolution operations. However, the key message to take away really is to understand the HPC footprint. So why is HPC necessary? And this brings us very quickly to the complexity of all the parameters, right? Hyperparameters, learning rate, how many neurons in one layer, how it all is actually the whole architecture constructed of the deep learning network. These are all questions for which the answer is not evident. You have to search essentially for the right architecture for certain problems. There are some, let's say, de facto standards, you would say, for image recognition, for instance, but still, when you really want to tune it for your application at hand, there are different ways how to do it. You have to understand that the hyperparameters play a big role here. And then from that, you quickly have also an understanding where the learning happens in the connections, in the weights of the whole networks, and we will talk about what the weights are. But then you also really see the growth of these weights over time, especially if you have different architectures, right? So we move from the perceptron with a couple of parameters up to a convolutional networks with lots of parameters. But however, by having more weights to train a smarter architecture, a smarter model in a way, of course, we can still do some accuracy improvements. However, machine learning in a way, we say as experts, is often not really 100%, very often. And this has to do with noise in the data. And I will show you some of the limits now, why the accuracy cannot be always 100%. Okay, but we start with the first part of the lecture now, and you see we fulfill finally some promises, even starting with lecture 1 here. So when you did this lecture, then you have essentially parallel computing understood on different levels. That means these abstractions that we have, again, you have a GPU there, very technical material. However, you will see that GPU will disappear in source code lines from TensorFlow and Keras. So this is another abstraction layer, right? Where you say, okay, TensorFlow is shifting around with lots of tensors, and that's where the learning progress happens. We will see that a bit in the backpropagation elements and so on. But this is then also, let's say, a little bit more further than abstracted by using Keras. And we will go into this and discuss it. However, when you master this, AI is used in many different approaches in scientific domains as well. So in one respect, it is an application of HPC. But in another aspect, you would also see it as an enabling technology for many, many scientific domain-specific applications that want to learn from data. That's what machine learning stands for, learning from data. And if you think about back what we said about physical modeling and what also Reza will teach you here and there in CFD coming up in the next couple of lectures, this is a bit different. You have, simulation sciences based on natural laws, numerical methods of physics. So this is then a complete different element in a way, but you would combine it today of saying also these applications would have data where you can further learn from. And or you can also think about the learning can be constrained with physics. So there are different ways how this really is now affecting massively the scientific domains, and our EuroHPC machines in the Union are really getting more and more workloads of AI applications on a daily basis. Hence, there are more programs, more application toolkits available, which brings us also to the HPC programming paradigms you see there, which is of course another factor here, how you really use that with high-level libraries, for instance, like TensorFlow and Keras we will do today. So again, we dive into the application field, and today we have now this artificial neural networks. I think some of you have heard this already, and we start with a very basic idea of this when we think about the learning progress, and this is something which we see as a supervised learning approach, meaning that it's one of the most simplest way how to learn from data. And this is given by having some input data, which could be a vector of different observations. But the key for supervised learning means we have a labeled data. So we can have for each of those a certain class or a certain, let's say, output that is definitively, connected to the input given. So every time you have a certain number of input in this, vector, you get a certain output. Could be one class, could be another class, etc., etc. Hence, you have this data in a very specific way, guided by the labels, as we call it, this label Y. And this enables us really to learn from data, let's say, very well, opposed to other elements, which unsupervised learning. There's also learning possible, but of course it is a bit more, let's say, cumbersome. And you have also other variants of reinforcement learning, for instance. So we stick here to the supervised approach today in order to understand prediction. So what could be predictions? Here's one example where you say you want to predict elements of this, and you would say, okay, I have already known there's this iris vitosa, and there's iris setosa, and there's this iris virginica. We know them from the images. We have this labeled data, as you see. So we have for this input vectors, which all of them have, let's say, two elements, a petal width and petal length, a data set, which is always labeled with Y getting green, and here getting, for example, visualized as orange, as iris virginica class. So two class problem. And now we have a new flower, a new data element, and we want to know, is this flower now essentially an iris virginica or an iris setosa? So this is not obvious, hence we'll have to learn it. And we learn it in a way by having a so-called decision boundary. And this is alluding to the perceptual learning model, the first start we will talk about, where you have one line that we now try to find in space. We move it around, so it's not clear that it's now at this position that you see there, but we will learn from data to establish sort of a decision boundary where we then can decide, okay, is it above or beyond, for instance, like here, and then take our decision that this is most likely a iris setosa here. Hence, you have a sort of mathematical notation now. If you remember a little bit how a line is looking like, you have here the summed up linear using weights part, the linear combination of this input data, the output that we want, and then of course the so-called bias that you also know a little bit of how the kind of the line is in the space. Then there's a nonlinear activation function added, which in our case is pretty simple when you have a binary problem, for instance. But this is a way how you would see is now this line in a very, let's say, abstract notation. You also observe the red elements here. These are the weights. And if you remember a little bit how that works, you see that this also will determine a little bit how the line is now moved across the space. And we can incorporate this a little bit in this by, simplify a little bit the math here by doing this in an X transpose way of using then the weights here as a vector, starting already with index 0 here. And then we have the much more compactor notation, right? I also showed you a little bit what that means here, vector W with all the trainable weights, or here the X data. Here it's important to understand that these are constants, right? What we want to change is, of course, now the weights of this line. So in other words, how it exactly would now the line be positioned in space to form the decision boundary. And there's a certain approach to it called the perceptual learning model. This is a relatively quick introduction, so we will, let's say, keep that to a moderate degree. But before we also go to that more in deep, we also want to have, let's say, a much more interesting, let's say, data set, which is multi-class. And here you see 10 class digits, 0 till 9 of handwritten characters that someone has written. And then the beauty is we have a labeled data set here. That means we know for each number that should be a 0, that should be a 4, that should be a 1, etc. Right? We have this data set a little bit already. It's 28 by 28 pixels here. In a way, again, sort of an image, but we have this as a nice data set available, and you can get this these days also actually directly out of Keras with your packages. So now when you look into this and think about the supervised learning process, we would separate the training set from the test set. So we have the whole training examples that you have seen with all the numbers, right? Always having this 28 by 28, which sort of creates the features with then the scale of the, you see here, of the grayscale making up the number. But we have also the label Y here, right? Like it's a Y label 2, label 4, etc. So what we want to do is now cut the data set to a certain degree in two parts, where we first train from, and then for checking really if you really learned very well, we use a testing data set. In more advanced machine learning applications, you would rather say we also need a validation data set, and or even many of them, because they're used for model selection. We don't do this here. We keep it to a very simple approach. But here you see that we now have this cut up in a training set and test set. Now for the lecture today, we will have a little bit a bias of one particular tool set, which is the TensorFlow and Keras tool. Keras is nowadays also inside TensorFlow, which are also introduced already to you, so I don't repeat it very much. Think about that Keras is a high-level abstraction, again, from the tensors that flow in TensorFlow, making it a bit more simpler to understand because you have a very nice way of understanding it again with layers. Then starting a little bit with real code and thinking how that could work is firstly machine learning. And, this starts always with kind of a data exploration step. So understanding the data first before you perform machine learning, right? You see here we do this in the train and test set as we discussed. This is data from the MNIST. And then we have a small sort of 2x loop where we want to just go through the characters and give them out to actually have them shown. And you see here a little bit that we do this now for the first 10 handwritten characters using this function here, and also show then always a label. So this would be a very simple Python script for data inspection and exploration that is there where we can find different elements out. Right, and if you do this, for instance, with something we call a Jupyter notebook. And the idea is that there's one final project for you, if you have interest, to use essentially this Jupyter, and also use machine learning. And this will be something then for those that are very interested in AI, they can go off and then will learn more there how to do it practically. But of course, there are also other topics available, as I was saying, with this fishing simulation and so on. Hence, coming back to here, Jupyter is really a nice front end to get Python code really into a very nice tool where you can edit very, let's say, effectively, really. Combined with visualization. So you have the same code here and you see how that looks like sometimes you have to switch to the right kernel here. Here's a conda TensorFlow example on one of the Jupyter ones. There's even your packages that you can download, and you can have it on your own system. But in the end, Jupyter will be also deployed on the HPC system, that what we also will use in the final project. However, a takeaway message is now, when we looked at it, we have a two-dimensional data set, 28 by 28 pixels. Okay. So now when we think about what we just learned with the idea of the linear really model that we have, this is a little bit now different to encode, right? We need somehow now to make this as a vectorization, to have this as basically as a one-dimensional input rather than a two-dimensional input. So this is something where now how it works is that we again have the input data now from all these different elements, and we need to think about how we get this two-dimensional data rather in a vector than in a two-dimension. So we vectorize this input data as a first step in order then to actually come with our equation to the output. Is it this or that? When you do this, you have a very long vector, 784, and this is the one-dimensional representations. Usually you would also think about reshaping in that sense combined with normalization, so that you have also not these high numbers here, because if you multiply them and so on and taking weights in the learning process, you quickly will be getting out of bounds and everything, let's say, out of capacity in the integers. When you stay with smaller numbers, you can, let's say, for mathematical convenience, compute them much better. But however, you mentioned also there's a loss of information, right? So when we have 2D to 1D, there's some problem of the neighborhood. So we lose a little bit the pixel, let's say, that are close to each other. And this will be one interesting step then we will have in part 2 when we talk about more convolution operations. Now, there's one thing that we also have to think about. The initial line I was showing you was a binary classification problem. We have to extend this a little bit to make it now a 10-class classification problem. So in the other words, the y that you had was let's say +1 or -1 for the flowers. This is something where we now have to extend to the number of classes. And by doing so, we can do this with a specific function. And this is a softmax layer that you usually always have here in the in the deep learning networks. It gives you output probabilities, and here we actually have then the probability to which class it really belongs. You see here nicely how Keras can create this with sequential, for instance. Then you add a model with a number of classes and the input shape that we just reshaped to the very long vector. Right, so we have this input here of the very long shape. We have the number of classes defined, so 10, and then we add this, activation function softmax, which gives us then the class probabilities, and then actually you have your model ready. By doing so, and we have now, of course, 10 times the amount of parameters. So because we have all of these parameters, and they have connections with all of these different, let's say, 10 elements that we put as input, plus 10 of the bias that comes from the equation in the beginning. There was always +1, if you remember. So you end up with 7,850 trainable weights, right? Even without a network having no layer whatsoever. It's just a multi-output perceptron model, a very simple learning model. Hence, when we continue this, we can now add also something which is now forcing the learning in it, which is the optimization step. So what we're searching is that these weights will be getting to a point that they, so to speak, fit the training set, right? So that the output given in the training set matches the inputs, and the weights will be adjusted over time. So you always update the weights depending on an optimization step. And what we do there is essentially what you see here, the SGD optimizer that you can use for it to, let's say, minimize the loss function that you can, specify. You see here a categorical cross entropy loss that you define, which is good for this multi-class problems. But then you have just this loss, and you want to, let's say, knock down the error by essentially using something called stochastic gradient descent, going down the slope here in the error of these functions. So this is a particular loaded question. So there are learning rates and other elements like, is it maybe the best optimizer? Is an Adam optimizer not better than this, etc., etc. So there are lots of, let's say, tuning elements in it, but this is a basic idea how the learning works. Of course, combined with backpropagation then through the different layers. Usually, as we don't have here the layers, we stick to this as an optimization step and see now the whole code of this particular example. So you would have here the number of epochs. It means how often you actually move through the data set, right? The whole data set. Then you have something like the batch sizes. These are used in each of the learning steps that you have while doing this inside all of these different epochs. So these are also different, let's say, configuration parameters that you have to choose from. Number of classes, we have our optimizer, and then you have here the test and training that was reshaped and then also normalized, as we have seen. So let's move to the other part where we then had our model that we created. You remember in a couple of slides ago, where we then also thinking about now's the time really to have so-called the learning process. Compile stands here firstly for creating now a, let's say, execution tree in a way to really leverage now the different nodes on the HPC system with the GPUs. So lots of things are now happening, mapping really this, let's say, problem to the lower layers and how you really execute it, right? And you see here, we want to get out some accuracy as a metric, could be also error rate. So metrics is one of it. And here you see then the real learning where it happens. You fit the training set essentially with your labels and your, let's say, input data. We had this batch size and we train the number of epochs in order to knock down the error over time with this error function using this optimization that we just heard. And what we get out by doing so is that over this 20 epochs, you get then something like maybe 0.92 as the accuracy. So in other words, more or less 92%. So this is quite nice already. I mean, it's a relatively small problem. And then you have to think about also that maybe we can do a little bit more if you train again and say we want to have more epochs, but be careful not putting 200, 2000 or something. So then you're in something we call perhaps overfitting. You learned each individual data point instead of, taking, so to speak, a very good learning curve through this. Otherwise, you really there's a highly likelihood that points which are sitting very closely will be misclassified if you overfit. On the contrary, if you just have one epoch, then underfitting will happening, right? We didn't learn enough from the data more or less. And this is also something which is, so to speak, a sweet spot now to understand how many epochs we have to do in order to do the training here. You see that the training relates again to the error that you have on the training samples. And of course, when you do it too much, you will see that, okay, the error on the training samples will be actually getting almost to zero. But the trouble is if you have the testing data set, which looks a bit different than the training set with other samples, it will follow suit in your error and say, well, it's indeed well learned, but at some point in time, when you have the number of epochs too much, it will start getting overfitted, right? So getting more errors again, and that's not good. So when we have this multi-output perceptron model, we can conclude we have around, let's say, 91% performance. And what can we do now without having any layers, right? So basically, we should do maybe extending this neural network, right? Maybe introducing layers. The question is how many hidden layers, how many layers you would add. And this is for us a dense layer, and this will be an important distinction to the second part we have later. So in other words, we had this one perceptron, which was just one of these nodes. If you remember the beginning, right? The inputs summed up linearly using weights, and then having this kind of activation function. Now the idea is to combine these, right, in artificial neural networks, making it a multi-layer perceptron then if you have different of those. And the hidden layer, of course, is also fully connected here to the input layer. That's important. And again, to the output layer. With this, you can solve also known problems like the XOR problem, that with one perceptron you basically can't solve. You see here 4 different data points, for instance, and you will not find one line that actually can separate them. And it's depicted here again. But when you consider, let's say, using 2 lines or combining these perceptrons together, you can have an interesting decision space here, really, of capturing then this XOR problem. Hence, you get a much more powerful way of combining them and also making able, let's say, sort of non-linear decision boundaries and non-linearities, as we call it. You see that a little bit here alluded to this. This is just one line in the space, and it's hard to capture this data. When you have, let's say, non-linear activation function, and then also the, let's say, more and more of these neurons together, this kind of perceptrons added together in something we call neurons per layer, you can come to quite some nice decision boundaries here, right? And coming back to our original one, you see here we would exchange then this kind of function with a specific function that you see here. The rectified linear unit, for instance, is very popular these days. Others coming along with a leaky ReLU. So these are elements we basically stick in here, and to make the whole, let's say, mathematical foundation much more able to catch these nonlinearities. And this is also one of the ideas why artificial neural networks are so powerful, because they can create quite sophisticated decision boundaries. Now, thinking about the neural networks at all and the basic architecture here for MLPs and this multi-layer perceptrons, again, you have this hidden layers and maybe another hidden layer and then the output layer, and then you have a sort of probability of the outcome. And the highest probability is usually taking then the outcome, or the winner takes all rule, as we call it, right? So this is something which comes out, and this is something what comes in. And all of these connections that you see here between this is something which is not clear. It needs to be learned to fit, right? So this is something where the learning algorithm will take place. You see here a very short idea how that works. When you move the data through this network, it's basically here. You have some kind of information that you point through, and then you will know here at the end, is it something where is it the right class coming out? If not, you backpropagate the error through this network. And exactly there's also where then the learning takes place, the weight updating phase. So this is a little bit like a loop. You see that here, very simplified, where you initialize all of these different weights randomly, and then you loop until convergence, or the number of epochs, as we discussed. And exactly now the gradients that we discussed, the learning, of course, now think about really large networks. Going down here again and again, following the lowest, let's say, curve of error, taking derivatives and compute the gradients is always a very computing intensive step. And once you have done this in the, let's say, path of the neural network, you will also update the weights, right? Which is also now something to consider in terms of memory. You need to have the weights somehow in memory to also update the weights of all these different connections. So, and by doing this iteratively again and again, you see here that we are going again through the number of training samples, and we have always the output that we can now check with the desired output that is really in the data set. So we have a way of really getting this error understood and can minimize this, which is now basically the point of this downhill operation with this optimizer. Now, we also see that when you have a too, let's say, small learning rate, you not really come to the local or global minima as it is seen here, right? You're stuck in a local minima. If your learning rate is too hard, too fast, then you also miss it. You're jumping rather than really trying to find the kind of lowest error. So having a learning rate that fits, as you see here, that makes it error, let's say, and finds the global error, or the lowest global error, is of course something then which is a sweet spot to find for yourself. It's not the learning itself. That's what you have to decide what the learning rate will be. So one of these hyperparameters you can steer. Now, when we add this, 2 hidden layers now, and we'll use now what I just explained a little bit with this, back propagation and so on, as the learning possibility with the optimizer. Still, This is something which is hidden here. You basically don't really see that this is happening. You just essentially construct now a neural network, which is a bit different that we had before, right? We have again a sequential, but instead of having now just one, let's say, neuron there, and then extending it with this multi-class neuron, we have now really n number of hidden layers with 128 number of neurons in each of these hidden layers. They are densely connected. That's why there's dense here. And we have an activation function, if you remember from the equation, that is now the rectified linear unit. And the output, or the last part, will be then also the softmax, giving us then again the class probability like we had already before with the perceptron. But now it's, of course, a much more sophisticated element, this artificial neural network, right? So looking on this a bit more in detail, if you then execute it, this would be around 97%. So we actually improved the accuracy. You see here just the same elements now all combined in a Jupyter notebook. And you see also we trained for quite some epochs. It's 200 epochs instead of 20 because they're much more trainable weights. And this will be also now our takeaway message from the artificial neural networks, right? Towards the end of the first part. We had our multi-output perceptron 20 epochs, around 91%. The neural network 2 in 20, the neural network with 2 hidden layers in 20 epochs achieved already 95%. So we already could improve this by having a very, let's say, more smarter architecture, more, capable architecture than before, but we pay the price for it in computing. You see 118,000 parameters to train, opposed to 7,800 or so. So much more computing is needed already to compute this, but this is not at all what deep learning will show us later. So here we talk still about that this can be done from a CPU, of course, depending on that architecture again. And you nicely see also summarized the parameters layer by layer by layer and so on. However, now thinking about all of this, there's a nice video that summarizes this, and I really had here a very quick pace for this machine learning introduction in a way. This is not at all really learning theory, elements you really need to know, which basically Höfting inequality, why we can learn even. So all of these foundations, of course, have been carved out here in order to focus a bit on the trainable weights and to show you some code that really runs without knowing any of the lower level details. However, to really do this in a practice with the new applications, I need to encourage you to really take deep learning or machine learning courses, right? So this is not at all enough, as it is a HPC course. I also would recommend you to finalize this here with looking at the video. It's a quite nice summary, also with the different ideas of extending the neural networks. We will continue then in the second part, essentially talking about deep learning. So see you then.